Hi, everyone. I hope you're doing well. Today, we're going to continue our discussion of quantum mechanics, and we're going to talk about a really fascinating topic, a famous one, called quantum mechanical tunneling. Okay? In tunneling, particles are able to leak through or pass through a barrier, even when classical mechanics would say that that transmission was impossible. Okay? Here, let's take a look at the situation and see if we can understand what quantum mechanics is telling us. Okay, to start with, sorry, I have to move some things around. To start with, let's just remember where we are. We've been talking about quantum mechanics in one dimension, and we developed Schrodinger's equation, which allows us to find the wave function for different situations. And we investigated free particles. First, a particle that just moves through empty space, where the potential energy is zero everywhere. And then a particle incident on a step potential, where the potential energy changes suddenly from zero to some constant value, U0. And we investigated two situations there. The first is the case where the kinetic energy of the particle is greater than the height of the step. In that case, we can get a partial transmission and partial reflection of the matter wave, meaning that there's some probability that the particle will be transmitted and some probability that it will be reflected. We also looked at the other case, where the kinetic energy of the particle is less than the height of the barrier. In that case, well, we eventually get 100% reflection, but something really interesting happens as well, we saw. The wave function penetrates into the barrier a little bit. That means that there's some probability that a measurement would find the particle within the barrier, even though classical mechanics would say that was impossible. Okay? The phenomenon we're going to investigate today is related to this, as we'll see in a moment. After we talked about free particles, we went on to talk about bound systems, or systems with bound particles, the infinite well, the finite well, and the quantum harmonic oscillator. But today I want to come back and talk about tunneling, okay? In our book, tunneling is actually in a different chapter than the rest of this, which is part of the reason why we've put it off. Okay, when we investigate tunneling, we're going to talk mainly about this problem called the barrier potential, okay? Which is like a step potential in that the potential goes from low to high suddenly, but then the potential steps back down from high to low after a finite distance. It's a barrier. That's the barrier potential. And we'll figure out the transmission probability for a particle incident on such a barrier. Okay, and then we'll look at some examples. So this is a really interesting topic, as you'll see in a moment. So the phenomena of barrier penetration that we talked about several lectures ago suggests that quantum mechanics may allow particles to pass through a barrier, even if the height of the barrier is larger than the kinetic energy of the particle. And we can imagine a situation like so. We have a barrier potential, this rectangular barrier here. We have particles incident from the left with some energy represented by this dashed line, E here. So E is less than U0. On the left side, the wave function looks like some kind of harmonic wave, sine or cosine or some combination. But when the wave enters the barrier, because the energy is less than the height of the barrier, the wave function becomes a decaying exponential, like so. However, if the barrier is thin enough, then the wave function will still have a finite value when we reach the other side. And then it suggests that we should, when we get to the right side, the wave function will once again be harmonic, corresponding to a traveling free particle. So that suggests that the probability of finding the particle on the right side won't be zero, okay? In other words, there will be some probability for the particle to tunnel through the barrier. Of course, classically, this is forbidden. Classically, if I have a particle that starts with some energy, energy is conserved, it can roll along this ramp, but as the potential energy increases, as it goes up the other side, it will come to a point where the potential energy and the kinetic energy where the potential energy is equal to the total energy of the particle. And at that point, the particle will be motionless, and this will represent a turning point for the particle. It will get to this point, but it can't go any farther. It'll turn around and be reflected back. And in classical mechanics, a particle with total energy E can never pass over a barrier of height greater than E. Okay? So this is a really interesting difference between these. So let's investigate this problem more carefully.